Hello everyone, welcome to the control systems. This is part 4 of lecture 9 root locus techniques. In this section we'll discuss how to plot the root loci with MATLAB. So in plotting the root loci with MATLAB, we deal with the system equation given by this one. Okay, 1 plus k numerator and denominators. If you remember, the denominator of the closed loop transfer function is 1 plus k or g s times hs. So this part, so it has this kind of form. Okay. And then the MATLAB commands commonly used for plotting the root locus is this one, r locus, and you need to give the numerator and denominators. And using this command, the root locus plot is drawn on the screen. Okay? And the vector k is automatically determined. And for the system defined in state space or locus, in state space you can use this function, this built-in functions. You need to specify the matrix A, B, C, D. Okay. Okay. And this comment is also available. Okay. So the user supply this gain if you want. Okay. So if you want to plot the root locus with the mark like O or X, it is also possible with these functions. O locus, and then plot this O with this O or X. Okay. Okay, let's consider the system below given by this function, and the question is this. So plot the root loci with a square aspect ratio so that a line with the slope 1 is a true 45-degree line, and choose the region between this. Okay. So you can see this is the functions, and you need to set the regions, okay, using this one. So v minus 6 minus this is x and this is y. X is specified as v, and x is square because you want a square. And for denominator, there this, right? So you can just define like this: a, which is this one. This is what you need to put it to work. So multiply this to this and multiply this to this. You have 1, 1, 0, and this is 1. The coefficient of this one 4 and 16. You can multiply this together using this built-in functions. Then you will end up have the denominator given like this. Okay. And you can also find the complex conjugates of the open loop pole loop like this. You may use this root and then specify p. Okay. And does the system have the following open loop 0 and poles given like this? And then in order to plot, you can specify like this. This is a code I given in the GitHub. You can go and download it. You need to have the numerators, denominator, all locus, and specify the intervals, the plot, the screen, axis and grid, which will grid the plot, and the titles. So this is the plot of the root locus. So how many poles? There are four poles. One, two, three, four, and one finite zero. Okay. And example two, if you consider the negative feedback system whose open loop transfer function defined like this, in this case there is no open loop zero, and the open loop poles the location at this point, and you can use this function. So you can see this is the plot of the root locus. And yeah, if you want to see, you can put 0 or x here or anything. If you want 0, you just need to put 0, and then you will end up having this plot. And you can also plot the root loci using smaller increments of k. Okay? And then in that case, you need to specify it yourself. Like this, you need to define k in this part. Yeah, if you want small increment of k. You can also plot it if the system is a state space form. For example, consider this system. Of course, you will have this matrix A, B, C, and D. So yeah, this all locus and A, B, C, D is a comment to plot the system which has the state space form. Okay, and you can also convert it into the transfer function using SS2TF as well. Okay, and so this is the programs you can use to plot. You can download it from the GitHub. Okay, this is the plot. Okay, so this will go from this to this. So start from the pole and end up at the 0. And this is the pole. This is the pole. It has the infinite 0. And there's also the relationship between this zeta damping ratio of the pair of a complex conjugate pole with this angle. Okay? This angle. And the relationship is given like this. This is angle is measured from here. This is omega d. If this is a pole, and this length is omega d, this is omega n's. And the damping ratio determines the angular location of the poles, and the distance of the pole from the origin is determined by the undamped natural frequency omega n's. The command script you already did, so it overlay line of the constant ratio, damping ratio, increment 0.1. Okay, like this. This is the value of damping ratio, but if you use sgrid, it will give you the increment of 0.1. Yeah, like this. This is very small, but you can use this code and plot it in your computer. And if only a particular constant, this zeta line, in particular, or a constant omega in cycles are desired, then you can use this. So in this case, it means S grid. This is, what is it? Okay, This is theta and this is omega n. So if you wish to overlay line of constant theta and cycles of omega n as given above to the root locus of the negative feedback system with this numerator and denominator, well, you can use this functions, this code to perform or to plot it. See, well, this only show this value. Okay, this is 0 0.5, 0 0.70, this 0 0.5 and 0 0.70, and omega n. Omega n is 0 0.5, 1 and 2. 0 0.5, 1 and 2. And if we want to omit either the entire constant this line or entire omega n cycles, we may use empty brackets in the arguments of the sgrid command, like this. So in this case, you want to see this, but you don't want to see omega n. Okay. Next, we'll discuss the conditional stable system. Please try to plot it by yourself, because I gave the code, all of this code in the GitHub, and you can try by yourself. Just execute it, or you can write by yourself if you want. Next, we'll consider conditional stable system. Okay, for example, consider this system, and well, you can plot it using this plot the root locus using these functions, and you will see this. So you can see this root locus come to the right half plane, this as well. And you know that only stable this the negative half plane, if the root locus, if the pole stay only in this part, the system will be stable. So what does it imply? This said that the system is stable only for limited range of value of k. Okay, for example, in this case, only k in this interval and this interval. Okay, here, and then when it reaches this interval from 12 to 73, it is unstable. In this interval, it's stable, and then when k larger than 154, it is unstable again. And yeah, the system becomes unstable if the value of k in this range. Okay. So this kind of system is called conditionally stable system. I mean, it's stable at some value and unstable at some value of k. So in practice, conditionally stable systems are not desirable. Okay? And it's dangerous, but does occur in certain systems. In particular, the systems that have unstable feed-forward paths, such as unstable feed-forward paths, may occur if the system have a minor loop. So it is advisable to avoid such conditions.